Hello, my name is Dr. Astronaut, and I'm here to talk about Young's double slit experiment of the wave particle duality. Under some conditions, a particle acts as a particle, and under different conditions, the particle acts as a wave. It was also noted that electromagnetic radiation sometimes acts as a wave, and other times like a beam of photons. In 1803, Thomas Young announced his double-slit experiment with light, which debunked Newton's corpuscular theory hypothesis. In Young's double-slit experiment, he shot a beam of light through two slits onto an opaque surface. What was shown was a series of bright spots and dark spots. The bright spots where there was constructive interference, which means that the waves added up, and dark spots where there was destructive interference, which means that the waves canceled out. This experiment showed that light behaves as a wave. This was significant because there was debate over whether light was composed of particles, which was according to Isaac Newton's corpuscular theory, or waves, according to Christian Huygens' wave theory. This discovery laid the foundation for wave optics, like lasers, and was crucial for understanding the electromagnetic theory. It also laid the foundation for quantum mechanics, and it also has a conceptual impact, such as thought experiments involving quantum entanglement and the role of the observer in quantum mechanics. The experiment was also performed with beams of electrons. In 1924, Louis de Broglie stated a hypothesis that electrons and other particles behave like waves. According to de Broglie's hypothesis, photons and massive particles must satisfy a common set of relations that connect energy with frequency and linear momentum with wavelength. And here are the two equations where they were linked, where energy equals Planck's constant times frequency, and wavelength is equal to Planck's constant divided by the linear momentum. In 1961, Klaus Johnson performed the double-slit experiment with a beam of electrons, which showed a similar pattern with that of light, which confirmed that electrons behave as a wave. In 1974 and 1989, experiments were performed using single electrons by Giulio Pazzi and Akira Tonomura, respectively. Interference fringes were formed gradually, which also confirmed the wave-like behavior of electrons. And this right here is a computer-simulated version of the experiment with electrons showing the interference fringes, the constructive interference and the destructive interference pattern of the electrons as they came through one by one or as a beam. If I wanted to find the angle at which the bright spots are located from the slits, I would use the diffraction gradient equation, which is sine theta equals the nth order wavelength divided by the distance, which is the distance between the slits. The angular position of the nth order bright fringe is related to the separation between the slits and the wavelength. This is just an image showing this experiment done also, and you can see here that this is the first order wavelength, the second order wavelength, and subsequently there's a negative wavelength, first order wavelength, and negative second order wavelength as well. And this also shows the nth order wavelength of the destructive interference with the half wavelength and 3/2 wavelengths. Here are my references. Thank you.